kind of a it's almost a, what's the word I'm looking for? I lost the word. The opposite in a way. If one chord is a perpendicular bisector of another chord, one chord is the perpendicular bisector of another chord. It's not a very good picture. Then the first chord is the diameter. So you see this picture here. One chord is the perpendicular bisector of another chord. That means that first chord is the diameter. So here. All right. In the same circle or in congruent circles, if two chords are congruent, then their corresponding minor arcs are congruent. Okay, so I'm going to draw a circle here. That dotted line really has nothing to do with the picture. It's just in the way. Okay, so kind of look past that. So I'm going to say if two chords are congruent. So these two are congruent to each other. Then their corresponding minor arcs are congruent. So that means that this and this are congruent. And then the second part is just like the counter of that. It's if these are congruent, then the chords are congruent. If the arcs are congruent, the chords are congruent. So that's what we're working with today. Not too bad. Turn it over. Emily, put your phone away. In circle W, the diameter RT, here's the diameter RT, is perpendicular to US. Okay? Use the diagram to find the length of US. So, this is actually going to be theorem 11.4 because we're talking about diameter and perpendicular. The diameter bisects, don't write too big here because you're going to need the space underneath, bisects the chord. So let's look at what we have. If this is cut in half, and I need the total length, and I know that this is what, 16? Then I must say, okay, US then is equal to 16 plus 16, which is 32. Pretty easy. Okay, you all saying, when are we ever going to use this? I think this is kind of interesting. Let me show you something in the book, and I'm going to show you how they do it. Okay. So in archaeological digs, sometimes they find pieces of plates, and they like to be able to reconstruct what the plate looked like. Sometimes they make replicas off of it. But sometimes the plate isn't big enough to, the piece isn't exactly big enough to figure out what the plate, how big it was. So they can actually use chords and diameters to reconstruct the size of the plate. So that's what we're going to do with our protractor. Even Emily with her phone and texting. Do you want me to hold on to it for you? Put it away. So annoying. Well, I'm not saying it's not. It's just math is important too. Okay. So what I need you to do is, first of all, we're going to draw a circle, right? No, we're not going to draw a circle. Never mind. Don't do that. Draw two chords. So we're going to draw two chords that aren't too big. There's a chord, and here's a chord. They're not the same size. Something like that. Draw two chords. Okay? So, number 2, draw a perpendicular bisector. So this is where your protractor is going to come in handy. Let me show you. So you take this thing, and I'm going to try and draw a perpendicular bisector. So I'm going to kind of try and find the halfway point. I can see that I'm perpendicular if I line up this line right here with my chord, and I kind of try and find the center, and then I'm going to draw a perpendicular bisector with that chord. And then I'm going to do the same thing with my other chord. So I'm going to try and find the center and make sure that this line is lined up so I know it's perpendicular. Find the center and draw the perpendicular bisector there as well. So the perpendicular bisectors lie on the diameters and intersect at the center of the circle. So this right here is the center. Okay, so we're trying, in order to use our protractor to draw a circle, we need a radius. We can get a radius from our picture. Where would the radius be? From the what to the what? I know Ethan knows. Does anybody else know where the radius would be? Remember, chords lie on the circle, don't they? The endpoints of the chords lie on the circle. So where would the radius be? From the center to a what? I'll just tell you. From the center to an endpoint would be the radius. Okay, so the segment from the center to the edge to chord endpoint is the radius. Okay, so now I can draw my circle. Number 5. Use your compass to complete the circle. I think that's pretty fascinating that that's what they do. So let me show you how to do that. This part goes on the center. This part you kind of tighten down to here. So you have the radius there. And then you go all the way. My pencil doesn't work very good. You just take it all the way around. You try and keep that thing on the center. Cool. Isn't that cool? I think it's cool. Find the value of x. Well, we have not used theorem 11.6 yet. So we got to use 11.6. Okay? Okay. So here we go, you guys. Let's look at what we have here. We have arcs that are congruent. Arcs that are congruent. Let's go back and look at 11.6. It says right here, if two minor arcs are congruent, then their corresponding chords are congruent. Oh! These are the arcs. These are the corresponding chords. If this one is 12, how long is this one? 12. See how easy that is? Okay? So, the arcs are congruent. So x has to equal 12 because the chords are also congruent. Almost done. This is also 11.6 right here. In this picture, they tell us that these two chords are congruent. And x is right here. It's the angle measure. So if the chords are congruent and they're on the same circle, and this angle measure is 115, how much is x? 115.
Wow, this is so hard.
Not bad, is it?
Once I add more variables, just x, it will be harder.
It could be x plus 2 equals 115.
Or it could have x and y times both of them.
So, that's it. Is that doable?
Yes. Definitely.
Let's write down the reasons here, just real quick. Just so when you're looking.
Yes.
Chords are congruent. Arcs are congruent. Therefore, have you ever seen this for therefore?
Yeah.
Therefore, x equals 115 degrees.
Alright,